Hello, welcome to the course Electronic System Design. Last lecture we discussed about the CMOS inverter, which is a very basic circuit made up of two transistors PMOS and NMOS, and we saw that the voltage transfer characteristic of a MOSFET looks something like it starts from the high value, and as we increase the input voltage from 0 to high, this output goes from high to low, and we saw the various regions where PMOS actually turns off and NMOS actually turns on. So there are different regions where MOSFET is in, one is in saturation, one is in linear, one is completely cut off. So based on that we saw that it develops a voltage transfer characteristics which is output voltage versus the input voltage. So that is a DC analysis when we sweep the input from low to high value, how the output is changing. So that in DC analysis we do not consider the time as a variable, we only sweep the input voltage, and whatever is the voltage because of the resistive nature of these MOSFET, whatever is the voltage output, that is a stable value we get based on the input. When we do the transient analysis, when we apply a real signal on the inverter input, then the output actually responds to the input within a certain time. The output actually does not change immediately as we apply the input, but it takes time. So there is a inherent delay associated with all these devices, PMOS and NMOS. They take time, a significant amount of time, though it is very small, but it is significant. This amount of time is really needed for the output to respond to the input. So let us see today what are these delays, what we call them the delay of the circuits. So how the delays of the circuit look like and what are their definitions. So let us consider the circuit delays. So first of all, let us consider a simple inverter, and this time we are drawing the symbol of an inverter which looks something like this. Earlier slides we showed the schematic of an inverter which is PMOS and NMOS, but this is the symbol of an inverter. The input is V in and the output is V out. So now at this inverter we are applying a input pulse which is in time domain. So let us draw the input pulse first. This is the time axis on the x axis and the y axis is V input. This is in volt and this is your input waveform. So when we apply a pulse in time domain, actually this pulse is not an ideal pulse, it's a practical pulse. So it should have certain rise time and a fall time. So this slowly rises to a high value, stays high for certain amount of time, and then it goes down. So this is a single pulse which we are applying on the input of inverter, and this is your midpoint. This is 50%. of the final value, and this is your midpoint during the fall. Now let's see the output of an inverter, how it look like. The y-axis is now V out. Now the output for an inverter is actually inverted state of the input. For example, when the input is low, the output is high, as we can see from the VTC, the voltage transfer characteristic. So the out at time t equal to 0, or the origin, the input is low, it means the output will start from a high value, which is, let's say, here, and at this point we are applying a input pulse. So let's mark these regions. So these are the time instances when the input is changing its state. Now at this point we are changing the input from low value to high value. However, as we change the input, the devices PMOS and NMOS, they do not immediately respond to this change. There is an inherent delay in the devices, which, for example, turning on the device takes certain amount of time. The charge carriers need to have certain amount of time to respond. So the output actually does not change immediately. It actually responds to this input after a certain time. Let's say this is the point at which the output is changing its state from high to low, because the input is going from low to high. So this is how the output has certain amount of delay compared to the input, and this output will remain at low position till we are applying high at the input. At this point we are applying the input as low, we are bringing down the input from high to low. It means the output should go again from low to high, but it will take certain amount of time. So let's say at this point this is responding to this change and goes to high. So this is how an output waveform look like. Now let's see what are the delays and how do we characterize them in a circuit. So we see this point, which is the 50% of the input value. When input is changing from low to high and it reaches 50% of its value, from this time 50% of the output change, when output is changing from high to low, at midpoint of that, this is the midpoint of this output going low, the difference between these timings from 50% of input to 50% of the output, when the input is rising or the output is falling, that is called TPHL. We call it T. T is the time delay and the subscript is P. P is the propagation delay and HL. We call it TPHL, which is the delay or the propagation delay going from high to low of a output. So this much is the time we have in the going from high to low. Similarly, for the falling edge of the input, we have this 50% marker. So from this point to the 50% of output when this is transitioning from low to high, this time delay is called TPLH. The propagation delay while going from low to high for a CMOS inverter. So these are the TPHL and TPLH. These are two different delays which are called propagation delays of CMOS inverter. This we can notice one thing, going from high to low there is a different value TPHL. It depends on mostly on the NMOS, the size of NMOS. If NMOS is strong, that this delay can be smaller. And however, this TPLH, this is pulling the output from low to high. This mostly depends on the PMOS sizing, how strong the PMOS is. So these two values are little different, TPLH and TPHL. However, we want to have them kind of same so that we have a single delay in the rise as well as fall. However, these are slightly different. So the overall propagation delay, how do we specify? So the propagation delay TP we write as the average of both of these values, TPLH and TPHL. So this is TPHL plus TPLH divided by 2. So this is the average value of both of the delay, and that we call it the overall propagation delay of CMOS inverter. So these are the propagation delays. However, there are other delays as well. For example, how much time the output takes from going from high to low. So that is not dependent on the input side, but on the output only we want to measure how much time the output takes from high to low or low to high. So that value is called rise time and fall time. So for example, here the output is falling from top to bottom, so or the final the high value to the low value. So that this definition is like that. For a fall delay, when the output changes from, let's say, 90% of its high value to 10% of its high value. For example, this, if this is a 1 volt here, then 0.9, how much time it takes for the output to go from 0.9 volt to 0.1 volt, that is called the fall time of circuit, that we represented by TF. This is the delay between this and this. Similarly, for the rising edge, we have output is rising. So how much time it take in rising from 10% to the 90% of this final value. This much of time is called the TR, or the rise time, from here to here. So these are the rise time and fall time. So we discussed 4 delays. One is the rise time, one is the fall time, the other one is the rise delay, and the other one is the fall delay. So when we say rise time and fall time, these are only dependent on the output waveform, how fast the output is changing its state. However, propagation delay, or the normal delay we call it, rise delay and fall delay, these delays are dependent on the input various circuits, whatever is inside, how much time it takes for a transition to happen from input to output. So the complete circuit delay is called the propagation delay. So we have 2 propagation delays, one is the high delay and one is the low delay. Similarly, for a output, we have rise time and fall time. So let's write that definition in words. So rise delay let's first consider the rise time. We represent it by TR. Time to rise from 10% of VDD to crossing 90% of VDD. Similarly, fall time time to fall from 90% of VDD to 10% of VDD. And there is a single parameter to measure both of these, which is called the edge rate. T rise fall is nothing but the average of both of these rise and fall time. T rise plus T fall divided by 2. So this is called the edge rate. Similarly, we have definition for the propagation delays. First one is TPHL. This is the delay when output goes from high to low. When input is rising. Similarly, TPLH is the delay when output goes from low to high. When input is falling. And then we have a overall delay. It's called TP, which is nothing but the average of both of these values. So TPLH plus TPHL divided by 2. So this is the overall delay. So here are the definitions of the delays for a rise time, fall time, rise delay and fall delay. These are very much used in all the circuit design because we need to know how fast the output will be changing, and we have to design our successive stages so that they are compatible with the rise and fall of the previous state. Otherwise, there will be a mismatch in the voltage levels. So rise time is 10% to 90% it takes. We have not used from 0 to 100% because the 10 to 90% is the reliable range. However, from 0 to 10%, that is not very reliable range. We cannot consider that to detect a 0 because because of some various reasons that supply, let's say the output is not reaching rail completely, or it reaches the rail very after a very long time. We want to detect the output change, or the input of the successive stage should respond to that output change as fast as possible. So we want to define these noise margin, we call it, from 10 to 90%. In some cases, we also define, instead of 10 to 90%, we define 20 to 80% as well. So this just depends on our noise margin, how much noise margin we want to have. Based on that, we define these rise and fall time definitions. It can be 10 to 90% or 20 to 80%. It depends on applications. However, delay definitions are quite fixed. From the input when it crosses the 50% point to the output where it crosses 50% point, that much delay is called the delay of the circuit. And there are two types, one is the rise delay and one is the fall delay. So these are some definitions of the delays in our CMOS inverter. Now let's discuss something about the power consumption of a inverter, which is equally important as our timing delays, because the the power dissipation of a circuit can very much limit its applications in our electronics industry. If we have a circuit which is burning too much of power, then it may not be as good a circuit if we have a counterpart which is taking very less power. So power dissipation in a circuit is equally important, and for a CMOS inverter, let's see how many types of power dissipations are there in a standard CMOS circuit. The same analysis we can extend to other circuits as well. For example, NAND, NOR gates, or even more complex circuits. The same amount of, the same kind of power dissipation will be there in complex circuit as well. So first we discuss where does the power go in CMOS circuits. So this analysis is equally applicable for all the circuits. However, we are considering here in terms of CMOS inverter only. So the very first power dissipation which happens in CMOS circuit is the dynamic power dissipation. This dynamic power dissipation happens because of charging and discharging of capacitors. The second point where the power goes is short circuit current. So there exists actually a short circuit path between supply rails during the circuit switching. And the third power dissipation is the leakage. So this is because the parasitic components in the devices, there are multiple devices inside a PMOS or a NMOS device, for example diodes and parasitic bipolars and so many other junctions are there. Those junctions are also leaking some amount of current. So we have a leaking diodes and transistors there. So these are the three main ways of power dissipation in a CMOS inverter. Let's discuss them one by one. So the first one is dynamic power dissipation. So for this, let's draw the circuit of a CMOS inverter, but this time we will consider the load as well, because this CMOS inverter need to be connected to the next stage, which can also be a similar gate or the number of gates. So the input V in is, for example, changing, and the output will change accordingly. This output now is connected to another device which can be modeled as a capacitive load. We can model it as capacitive load because this connection is most of the time goes to the gate of another devices, and the gate of a MOSFET does not draw any current, it only offers the capacitance, the gate capacitance. That's why we are modeling or mimicking that load as a capacitive load, CL. So this is our node V out. Now in this circuit, we are applying a input which is going from high value to a low value. The input is initially high and the input is now changing to low. When the input is high, it means the output was low initially and the capacitor was discharged to ground, because NMOS was on and PMOS was off. So because NMOS was on, so the capacitance CL was initially at the ground state, or the voltage was 0 across CL. When we keep on decreasing the input, at some point this NMOS will turn off. So what will happen? This NMOS will turn off and this PMOS will turn on. So when PMOS will turn on, this output node V out will start charging from the VDD. So there will be a current flowing from VDD to the output node and going to the load. So there will be a current flowing from VDD to CL. So this will be the current path from VDD to CL, and this capacitance CL will start charging. Now the charging does not happen immediately because this capacitance is there and there is certain resistance in the path of this current which is offered by the PMOS. This PMOS exhibits certain amount of resistance. So because of this resistance and capacitance, there is a kind of time delay and the time constant is RC. So there is a delay in charging this capacitor and it takes little amount of time, let's say like this, the output rising, taking some time, and then it settle down to high value. So this is how the charging of load look like. Now the energy per transition, if we write for this circuit, is CL, which is the load capacitance, multiply by the VDD square. This is the voltage which finally appears across this capacitance. And the power we can write energy per transition into the frequency of operation. So we write energy per transition multiply by the frequency of operation, that is F, which comes out equal to CL into VDD square into F. This is a very standard formula for power dissipation in dynamic case, CV square F. So if we see closely this formula, we can deduce that this is not a function of transistor sizes. So this does not depend on the size of PMOS and NMOS. However, it depends on the load capacitance, and this load capacitance is nothing but the sizes of next stage inverter or any other circuit, whatever is connected to this. So this CL is nothing but the gate capacitance of the successive stage, which is again the capacitance of PMOS or NMOS gate. So this is not a function of this PMOS and NMOS, but the function of the whatever is the successive stage of this inverter. And to improve on this, we need to save the power in dynamic case. We need to reduce CL VDD and F to reduce power. So here we have this CMOS inverter which is driving the another stage. That another stage can be modeled as a load capacitor to this CMOS inverter. Now the energy per transition is CV square, and if we calculate the power dissipation in dynamic case, that is CV square multiplied by the F, which is frequency. So we have the formula for dynamic power dissipation, which is CV square F. Now to save the power in electronic circuits, what we can do to save the dynamic power, especially here. So we have now three parameters. First, let's discuss this one by one. The first one is the CL. The CL is nothing but the gate capacitance of the next stage. So this depends on many factors. For example, how much is the size of next stage, PMOS and NMOS, and how many gates we have connected. For example, we are connecting 5 inverters to this inverter. So the 5 PMOS and 5 NMOS gates are connected to this CMOS inverter. If we reduce the number of gates, we lack on the functionality. For example, this inverter, if it is not driving 5 gates, then we have to put another buffer and then drive those extra gates. This increases the complexity of the circuit. So it is good to have high fan out. This is called fan out, the number of gates we can connect to this circuit. So if we want to have high fan out, the CL is going to increase. So we want CL to be as high as possible to connect more gates, but for power dissipation point of view, the CL should be reduced. So we should connect lesser and lesser gates. So there is a trade-off between the power dissipation and how many gates we can connect, or the fan out of the circuit. The second element is VDD. So to reduce dynamic power dissipation, what we can do? We can reduce the supply voltage, VDD, and we see this is CV square F. So VDD is in square terms. So we reduce a little bit of VDD, the power dissipation will go down very significantly. But the problem is, if we bring down the power supply voltage and we have a threshold voltage which is generally a fixed number, it does not decrease, then there is very less difference between the threshold voltage and the power supply of a circuit. Then we lose on the noise margins. We cannot reduce the power supply without reducing the threshold voltage. However, if we reduce the threshold voltage, the leakage power actually goes up, because threshold voltage is the voltage above which the transistor turns off. Below that, there is a subthreshold leakage. If we bring down the threshold voltage, that subthreshold leakage will increase and we lose on the static power dissipation or the leakage power dissipation. However, we can save on dynamic power dissipation. So there is a trade-off between dynamic power dissipation and the leakage power dissipation. So this is second factor. The third factor is the F, which is our frequency of operation. If we reduce the transition activity on the circuit, then there will be less dynamic power dissipation. But it means that we are not operating our CMOS inverter. We are supplying a signal which is very less in frequency. However, we want higher and higher speed of all these electronic circuits most of the time. So reducing this F is also not a very good option, because we are losing on the functionality or the capability of this CMOS inverter. So these are the three terms which makes up the dynamic power dissipation. Now let's consider the other type of power dissipation. The second one is the short circuit currents. You can say short circuit power dissipation. Now let's draw this inverter again. This terminal is V out and we are connecting a load here which is CL. Now at V input, we are applying a high to low transition, and similarly output rises from low to high. Now what happens, we have here VDD, which is supply voltage, generally a high value, and this is the ground, which is 0 volt. When we are applying a transition from high to low, there will be a point where this PMOS is also on and this NMOS is also on. For example, let's talk about this point right at the midpoint of the input value. The input is not very high and not very low. If it is very low, then NMOS will be off. It is very high, then PMOS will be off. But when input is in between, when this is not completely high or completely low, then this PMOS is also on and this NMOS is also on. During this time, we have a path from this VDD to the ground, and the current will flow from this VDD to ground through these PMOS and NMOS. Of course, they will have some resistance in between, but there will be a short circuit current flowing from VDD to 0. If we plot this current graph, it looks something like this. On the y axis, let's say we have the current through VDD, and on the x axis we have input voltage V in, and this leakage current or the short circuit current, it looks something like this. So at very low value, this current will not be there. At very high value also, it will not be there. But during the transition, when this input voltage is not very high and not very low, it achieves a peak, and this current flows from VDD to ground. So during transition, there is a short circuit current. From VDD to 0 or to ground. So this is second type of power dissipation. Let's see the third type of power dissipation, which is the leakage power dissipation. Let's draw the CMOS inverter again. So in this case, we have this inverter and we put the input to a static ground. We connect the input to 0 and then we analyze the circuit where the leakage current is there. So this leakage current is there because the materials and whatever we use for this processing, these are not ideal materials, these are real materials and they have certain amount of leakage. So that leakage we want to measure by putting inputs as 0. So now we have junction connected to this V out node and then there will be a drain junction leakage. And there will be a sub threshold current. Because if we see here, we are putting input as 0, it means the output will be a high value. This PMOS will be on, this NMOS will be off, and this node will be VDD, which is a high value. Now this voltage will try to discharge through a low impedance path to ground, and this path can be through NMOS or through some junctions which are connected to this node. Through this NMOS, though this NMOS is off, but there is a sub-threshold leakage current available in this in NMOS because of the finite threshold voltage of this MOSFET. And this sub-threshold current is one of the most compelling issue in modern day technologies, because as we scale down the devices, we are also scaling down the power supply to save power dissipation or dynamic power dissipation. However, if we are shrinking down or reducing the supply voltage, we also have to decrease the threshold voltage. Then the threshold voltage is decreasing, it means the current will be there, the leakage current in the MOSFET. If we have higher threshold voltage, it means when the device is off, completely we are reducing this low leakage to a very low number. But if this threshold voltage is not very high, is a small value, then we cannot turn off the transistor very well. And this leakage current is one of the most compelling issue in modern day technologies. Let's write it down. The sub-threshold current is one of the most compelling issue in low power circuit design. So in this lecture, we saw two things. One is the delay definitions and one is the power dissipation. So these two parameters, one is delay, one is power dissipation, these are always contradicting each other, and the product of these two parameters is generally a constant. If you increase the delay, the power goes down. If you decrease the delay, the power goes up. So, the multiplication of this is called power delay product, which is a constant number for a technology. So, delay we want as low as possible so that we can achieve higher and higher speed. However, to achieve a low value of delay, you have to increase the power dissipation, which is a bottleneck for modern day technologies, because in modern day technologies we have billions of transistors in a very small area. If each transistor burns, let's say, X amount of power, then we have 1 billion transistors which are burning this X amount of power, which is cumulatively very high. So, we cannot handle that much of power dissipation burned in a very small area. So, we need to keep power dissipation as a low number, but if we keep that, our delay also goes high. Delay goes high means the frequency of operation we cannot have very high and the circuit becomes slower. So, there is always a trade-off between delay and power dissipation, and we saw there are three types of power dissipation. One is the dynamic power dissipation, which depends on CV square F, and then there is a short circuit current in the inverter. The same kind of current will be there in other circuits as well, and then we have a leakage current, which is nothing but the sub-threshold leakage which is happening in the MOSFETs, and this is dominant in the modern day technologies because we are trying to reduce the power supply. But if we reduce the power supply, threshold voltage also need to be reduced, and because of this low value of threshold voltage, the leakage current goes higher. So, these are some analysis about inverter circuits, and the same analysis we can extend to any complex circuit, NAND, NOR gate, or even the higher transistor counts. So, that is all for today. Thank you.